So that was the first method of obtaining the solutions for recurrence relations using generating functions. And next, we are going to see how to obtain the solutions using characteristic equation. And of course, we'll start with a simple case. Again, consider the homogeneous recurrence relation Tn equals C times Tn minus 1. This is a linear, constant coefficient, homogeneous recurrence relation of order 1. And we have already seen that the solution is C to power n times T0. Well, in our example earlier, we also had plus b here, but if you set that b equals to 0, this is the solution you have. Now, is this solution, this exponential function, some constant times, again, some real number to power n? Is it a typical form for linear constant coefficient homogeneous recurrence relations? This is going to be the key here using characteristic equations. Now, assuming that it is, we can actually plug this in a recurrence relation and see how it behaves, and then infer the properties of the solution. So the first, the recurrence relation with degree 1 was simple. So let's look at the next one, second order recurrence relation. Tn equals C1 times Tn minus 1 plus C2 times Tn minus 2. Now here, at this point, I have a hunch about the solution. It could be an exponential function because that was the form we have seen all along in all of the solutions. If you remember, we had some coefficient times some exponential function, right? 2 to the power n, 3 to the power n, etc. Whatever the coefficients were. So here, I'm going to assume some function k times r to power n for some k value, for some r value, which are real numbers, to be a solution. And to try this, just plug in this function into the recurrence relation. So into Tn, just put k times r to n. Into Tn minus 1, I need to put k times r to n minus 1, right? Because k is a constant, and r to n becomes r to n minus 1. And C1 is the coefficient, plus C2, k times r to n minus 2. Now you see all sides have k. Therefore, I can cancel k out. Okay, and I can also gather r to power n minus 2 terms. So what I have here is r to power n minus 2 times r to 2 equals, on the right hand side, I have r times n minus 2 parentheses. I have C1 times r, because multiplied with r to n minus 2, I get r to n minus 1, plus C2. And I cancel these out because, well, I'm looking for some r value here as a real number. As long as it's not 0, I can cancel them out. And what is left here is r squared minus C1r minus C2 equals 0. So if k times r to power n is a solution, then this r value is going to satisfy this equation, r to power 2 minus C1r minus C2 equals 0. You see, in this equation, what I have is the coefficients of this recurrence relation. And this we call the characteristic equation of this recurrence relation. Okay, so this applies only to constant coefficient recurrence relations, and this is the reason if you have functions here, I cannot find unique roots. Okay, so what does this tell me? If I can find the roots to this equation, functions of the form k times r to power n, where k is some coefficient and r is a root of this characteristic equation, is a solution. But you see, in the first order case, in the recurrence relation with degree 1, my characteristic equation is going to be r minus c equals 0. So the root is c. It's a first order equation, therefore there is a unique and a single solution. But this one, this is a quadratic equation. So what we know from basic algebra is that there will be two solutions to this. And in a general sense, if your recurrence relation is of degree k, your characteristic equation is going to be of order k, and it will have k solutions in the complex plane. Therefore, so this is the general picture for the linear constant coefficient homogeneous recurrence relation expressed here. The characteristic equation is r to k minus c1 r to k minus 1 minus c2 r to k minus 2 dot 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 minus ck equals 0. And this equation has k roots, possibly with multiplicities, so we might have repeated roots in the complex plane. And if the characteristic equation has k distinct roots, which is the simpler case, r1 through r sub k, the solution is going to be of the form k times k sub I times r sub I to power n, summed from I equals 1 up to k for degree k. Okay, and the coefficients k1 through k sub k are coefficients to be determined from initial conditions. So this is the reason for a degree k recurrence relation, I need k initial conditions. Okay, so there are some common mistakes here, some pitfalls maybe I can point out. For instance, take the recurrence relation Tn equals 3 Tn minus 1 minus Tn minus 2. So the characteristic equation for this is not r to the power 2 plus 3r minus 1 equals 0. So a common mistake is, well, this is 1. This will refer to r squared, but this will be the coefficient of r, and this will be the coefficient of 1. That's not the case. You see we have minuses here because you actually put them to the left-hand side. So an easier way to see this is you just write this as Tn minus Tn minus 1 plus Tn minus 2 equals 0. And from this, you can simply write the characteristic equation as r squared minus 3r plus 1 equals 0. Okay, so be careful about the signs. That's the first warning, let's say. The second one, be careful about the indices. Example, Tn equals Tn minus 1 plus 2 Tn minus 3. So some students, when they just look at this, they just look at the coefficients and write the characteristic equation as r squared minus r minus 2 equals 0, which is not true because you see, this is the recurrence relation of degree 3. This is in fact Tn equals Tn minus 1, or 1 times Tn minus 1, plus 0 times Tn minus 2, plus 2 times Tn minus 3. So the characteristic equation for this recurrence relation is not this, but r cubed minus r squared minus 0r minus 2 equals 0. Okay, and you should have 3 roots because this is a recurrence relation of degree 3.